Looking at errors and uncertainties then, the headings under which I'm going to look at, we have types, we have ways to express them, and we have the handling of uncertainties. So, in terms of types and ways to express them, we have random, we have systematic, terms which should be familiar to you from GCSE. And in terms of ways to express them, we have absolute uncertainties in values, in measurements, and we have percentage uncertainties in measurements. And we handle each of these differently. We can work in absolute, we must work in absolute uncertainties for some calculations, but for the overwhelming majority, we work in percentage uncertainties. And you'll see why shortly. So those are the headings for the work that we're looking at today. So what do we mean by random and systematic? Well, a random error or uncertainty is one which could be positive, could be negative, could be of different sizes between measurements. So if you were measuring a particular quantity, a random error in that quantity, the first measurement, it might be too big, the second one, it might be too small, the third one, the difference in the uncertainty might be greater in the third one than the fourth one. So there is this variation in the size of the uncertainty and whether it's positive or negative. So a parallax error, for example, if you imagine looking at the level of liquid in a measuring cylinder. So of course the meniscus is here. Now if your eye is up here for the first measurement, so you're looking down on the meniscus, you'll have a different error compared to if you are looking up. These of course are extreme examples. You wouldn't do this. You would always try, of course, to have your eye level with the bottom of the meniscus. But you are making a judgment in this. So your eye might be here, it might be here, it might be here. You're making a judgment, and that judgment will cause a randomness in the uncertainty. Sometimes it will be too big, the measurement that you make. Sometimes the measurement will be too small relative to the true value. And the amount by which it varies will vary. So that's a random uncertainty. And all human errors are going to fall under that. So you have random and you have systematic. Now systematic is out by the same amount in the same direction every time. So a zero error is a classic example of that. Using a balance to measure the mass of something in the lab, if you don't zero the balance first, then maybe you have a systematic error there where the readings are all 0.01 grams too big or too small, but that won't change. Or if you're measuring something, the mass of something, and it's in a beaker, you're measuring the mass of a powder or a liquid, and you don't put the beaker on first and zero the balance, then all of your readings will be too big by the mass of the beaker. That's a systematic error. So you have random errors, you have systematic errors. And how we treat those then is different. So, absolute and percentage uncertainties or errors. So an absolute uncertainty, for example, in length, a 1 meter ruler marked in millimeters, you will have plus or minus 1 millimeter in your values. You can read to half a scale division, so you have I just go back and look at this. You have a ruler and you're going to measure the length of something using that ruler. Well, your ruler is marked in millimeters and you can read to half a scale division over here, so that's almost on that one and that is almost on that one. So you have plus or minus half a millimeter either end, and so you would have plus or minus 1 millimeter in your length. So the plus or minus 1 millimeter, that is the uncertainty in the absolute uncertainty in your length. So generally speaking, if you have a measurement x, the absolute uncertainty in x is delta x. Percentage uncertainty, well, if you had a length of 10 centimeters, a measured length of 10 centimeters, and you had an absolute uncertainty of 1 millimeter, delta L, then the percentage uncertainty is the 1 millimeter over the 10 centimeters, which would give you 1 in 100, 1%. So generally, percentage uncertainty in x, delta x percentage, is delta x over x times 100. That's obvious, I hope. So why do we bother with that? Well, the thing is that your value of your absolute uncertainty is not terribly useful in itself. If you look at this measurement of the length plus or minus 1 millimeter, that's all very well, that sounds fine. But then if you say, but the length I'm measuring is 1 millimeter, then what you have then is a 100% plus or minus uncertainty in your value. Whereas if the length is 1 meter with the same absolute uncertainty, then your percentage uncertainty is 0.1%. So you see that the percentage uncertainty is a much more useful measure of the impact of your error on the values that you're taking. Looking then at the treatment of absolute uncertainties. Let's look at an example of absolute uncertainties. So let's say here we have a pendulum. The pendulum is suspended from the ceiling and we can't get at the ceiling then to measure the length of it. But what we can do is to measure the distance from the floor to the centre of mass of the bob. So what we have then is that the length of the pendulum will be h minus x. So the uncertainty in our length is the uncertainty in our height plus the uncertainty in x, which is likely to be plus or minus 1 millimeter in each case. So the uncertainty in the length will be the sum of these two. Equally, if you were to say a similar kind of thing where the height then of the room was L plus X, you would have the same thing with the uncertainty in H is the uncertainty in L plus the uncertainty in X. So for sums and differences, you have adding the absolute uncertainties. In the quantities. So if, for example, L equals L1 plus L2, then the absolute uncertainty in L is the absolute uncertainty in L1 plus the absolute uncertainty in L2. Equally, if L was L1 minus L2, then we would also have delta L is delta L1 plus delta L2. So that is how you deal with uncertainties in sums and differences. Now, of course, you could go on to say then that the percentage uncertainty in L is the absolute uncertainty in L over the value of L times 100. And that's what you would do. But my point is that your first stage is doing this, working out the absolute uncertainty in your sum or your difference, and then working out the percentage uncertainty that represents. So that's absolute uncertainties. Now, that's easy enough to do, and it's a stage in the overall treatment of uncertainties. So if we look at percentage uncertainties then, well, this is everything else we use this for. All other mathematical functions. So products, quotients, exponentials, all work like this. So, for example, if we said A equals B times C, then we have the percentage uncertainty in A is the percentage uncertainty in B plus the percentage uncertainty in C. And if I'd been thinking, I'd have done that in red. So we are adding percentage uncertainties. Previously we added absolute uncertainties with sums and differences. With everything else, we're working with percentage uncertainties, and we're adding them together. So if we had A, do it in black again, A equals B divided by C, then again we have the percentage uncertainty in A is the percentage uncertainty in B plus the percentage uncertainty in C. If we had A equals B squared, then you'd end up with the percentage uncertainty in A would be 2 times the percentage uncertainty in B. Just like this, really. So that generally leads us to, if A equals B to the n, then we have the percentage uncertainty in A is n times the percentage uncertainty in B. So the percentage uncertainty in the area of a square would be twice the percentage uncertainty in the length of the sides. The percentage uncertainty in the volume of a cube would be 3 times the percentage uncertainty in the length of the sides. So percentage uncertainties then are the most commonly used. And I should say at this point that all we're doing is looking for a feeling for the uncertainties. We're not rigorously establishing them in some kind of statistical manner. This is just a broad impression of the uncertainties. And all we have done so far is to look really at single values. We haven't looked at how we deal with uncertainties from empirical data, where you have 3 or 4 measurements of the same value. How do you deal with that? That's what I'm going on to next then. Looking then at how to deal with ranges of data, you would normally in an experiment, you would repeat your readings, and so you would get, let's say your values of x would be x1, x2, x3. Now, your uncertainty in x, your percentage uncertainty in x, would be half the range of x over the average times 100. Now, of course, within this, you're going to remove any anomalies before you do your range and average. But this, of course, is a far better measure than the percentage uncertainty in any given value. You can work out the percentage uncertainty in x1, but that doesn't really tell you a reasonable measure of the uncertainty in your measurements of x, because that's only one value. It's only taking account of the errors involved in that one value. You've taken 3 values and you've taken an average. You've plotted your average then in your graph. So the range of values of x gives you a much better measure of the uncertainty in x and the percentage uncertainty in x as a consequence. So that is how you deal with ranges of data. Now I want to pull the knowledge that we have gained so far together into one worked example. So I thought I would take one that we're maybe reasonably familiar with, calculating G by using a simple pendulum. We should know that the period of a simple pendulum is given by 2 pi root over G. So we always want to plot a straight line if we can, and if we're going to find G here, then we're going to get rid of the squared. So if we square everything, now we have a relationship that is t squared proportional to L in the y equals mx plus c, but in this case c is 0. In the y equals mx form, you've got t squared equals 4 pi squared over G times L. So t squared proportional to L is what we've got here. So if we plot this graph, the gradient of the graph will be 4 pi squared over G. We know pi, so we can get G from that. So that's the experiment. That's the general principle in doing an experiment. You want to get a straight line if you can, if you're trying to demonstrate proportionality. That's what you do. So that's what we're going to do. Let's look then at some sample data for this. I have only taken one value of length, and I have made up some values of the time for 20 oscillations. Now, again, we take 20 oscillations rather than one, because in each timing, if you imagine the time it takes, your pendulum is pulled out to one side and you started swinging, and when the pendulum gets to here, you start your stopwatch, you say 0, you start your stopwatch, and then you go 1, 2, 3, 4, and so on. Now, if you just to go 0, 1, then the uncertainty that there is in the starting and the uncertainty that there is in the stopping, if you think about it, your reaction time, the time it takes you to realize, oh yes, it has passed the equilibrium position, now it is time for me to start the stopwatch, so I start the stopwatch. And likewise, when it comes back, it has passed the equilibrium position, and after the first oscillation, it is time for me to stop the stopwatch, and so you do. So there are definite absolute uncertainties in those timings, or that timing. And it doesn't matter whether you do one oscillation or 100 oscillations, your absolute uncertainty is the same. So if you take 100, then the absolute uncertainty in your period will be the absolute uncertainty in your measurement divided by 100. This is why we do 20 oscillations or 40 or whatever. And the choice of how many you do is largely a practical one. Partly you're saying, I want to take enough oscillations so that I reduce the impact of my absolute uncertainty on my period. But also you're saying, I want to finish this in my lifetime. So you're looking for times in the order of 30 seconds to a minute. Or 10 oscillations. I wouldn't go below 10 oscillations in my experiments generally, but 30 seconds to a minute for our measurements is a reasonable thing to do. So I've said the length of the pendulum is 1.00 meters, and remember, because I have 3 sig figs in here, I will have 3 sig figs everywhere in this column. Every piece of data in this column must be the 3 sig figs. Likewise, I've got 4 sig figs in each of these, and therefore each of these will be to 4 sig figs. And likewise here. So, I've got 41.02, 40.57, 40.32, 40.63, and I have an average then, if you add them all together, (41.02) plus 40.57 plus 40.63 divided by 3, an average, oh my apologies, I shouldn't have done that. I have an average of 40.63 for those 3. Again, 4 sig figs. So 40.63 divided by 20 gives me 2.0312. And a t squared of 4.127 seconds squared. Notice the units, I have to have my units in my header. So what we want to do now, of course, is to work out the range of t, which will give me my uncertainty in 20 t's, and then it will give me my uncertainty in the period, which I can use to work out the percentage uncertainty in the period, which I can use to work out the percentage uncertainty in the period squared. That's my sequence of events. So the range of t, well, the biggest value of t I've got is 41.02. My smallest value is 40.32. So my range then is 0.7. So my uncertainty, remember, is half my range. So that's 0.35. So that's 0.35 is the uncertainty in 20 oscillations. So 0.35 divided by 20 is the uncertainty in my period, which is 0.0175. So my percentage uncertainty in t is 0.0175 divided by my period, 2.032. And that is 0.86 or thereabouts. Not 0.861 3 sig figs. And of course, my percentage uncertainty in t squared is 2 times my percentage uncertainty in t, which then gives me 1.72%. So, you see how I have said I want to reduce my uncertainties, or the impact of my uncertainties, both really. So I take 20 oscillations, not just one. I take 20 because it gives me a reasonable period of time. If it was a very long period, if a pendulum was very long, I would aim to time for 10 oscillations. But I'm looking for between 30 seconds and a minute for each of my measurements. I have worked out my average, I've worked out my period then, I've worked out t squared, and I've been careful to keep my sig figs consistent. I've got 4 sig figs here, I can do 4 sig figs here and here then. But I must have 4 sig figs all the way down in these columns because that's what I've got. 3 sig figs here, 4 here, 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 here and here. So in order for me to work out the percentage uncertainty in t squared, which I'm going to need, I use half range over average to get, I use half the range to get my uncertainty in 20t. I then work out the uncertainty in 1, which is 1/20th of that. Then work out the percentage uncertainty in t, and twice that is the percentage uncertainty in t squared. So that's how I would use those. Now another way to look at uncertainties is graphically. So imagine you've taken all your data, you've got all your values of t squared, you've got your values of L, you plotted your points. Now, I've got, let's call this graph 2, and let's call this one graph 1. So what I have done here is I have drawn the error bars. This one's not quite right. This isn't based on real data. So what I would have done would have been to plot my points, and I would have worked out the maximum and minimum values that each value of t gives me. So I'd have said my percentage uncertainty in t squared here is, therefore my t squared could vary between this value and this one, and put my error bars on. Likewise for each of these. So now I've got the extreme values for each of my values of t squared. I can then put lines of best fit through my points. One with the steepest gradient I can, one with the shallowest gradient I can, whilst going through the error bars. Ideally, you want to just touch some of the error bars, top and bottom, so that you are genuinely doing the biggest and the smallest gradient you can. So now, your uncertainty in your gradient would be gradient 2 minus gradient 1 over 2, half the range. And of course your gradient is 4 pi squared over g. So you can then say that the percentage uncertainty in your value of gravity, I better call it gravity since I've called it the gradient g, is the g2 minus g1 over 2 divided by the average. So this is another approach, and you can see how in doing this you're taking into account all of the uncertainties. You're using the range of values you got for your t, and you're using that to work out your period, and therefore your period squared, and the uncertainty, percentage uncertainty in t squared, which allows you to work out the max and min values for each of the t squareds, which allows you to put your error bars on, and then you can put in your biggest and smallest gradient that goes through those error bars. Now, you might say, well, you said all of the uncertainties and you haven't, have you, because you haven't considered L. I haven't put the error bars on for L simply for clarity, but you certainly could have, and you would have, your error bars for L in every case, your max and min values for L, which of course is easier. So, you have seen what absolute and percentage uncertainties are. You've seen that we have uncertainties due to systematic and random effects. You've seen how to handle absolute and percentage uncertainties. You've seen how to do percentage uncertainties with a range of data. You've seen those principles applied in this particular example, and you've also seen how to use the graph to get the uncertainty in G.